Hello everybody, I hope you all are doing great. I welcome you all to this interesting series on system design. So in this video, we'll discuss about the leader elections for auto recovery in the distributed system. So as the statement suggests here, consensus in the chaos. So what does that mean? Like if we take a simple example, that is making a decision during a normal time is very easy, but making a decision or an agreement during a wartime or during a default situation is difficult. So that is exactly what we'll discuss in this video, where like choosing a database or choosing the servers before the production is very easy. Like we can just predict a couple of numbers and we can just do that. But choosing a server or deciding the things when the application is in the production is something difficult, right? So that is what we'll see here, how we can implement an auto recoverable mechanism within the servers, so that we don't need to have a manual intervention in middle of a chaos within the nodes or the servers. So in this video, we'll see the mechanism of leader elections, auto recovery, and preventing the split brain in the distributed systems. So here, first of all, let's understand what is a single point of failure. So for that, let's take a simple example. Let's say we have multiple databases. So let's say we have a single database that is accepting reads and writes, and due to high load, we have increased couple of more instances as a read replica. So now in this case, this is the only leader that is accepting the reads and write, and we have decided it manually. But due to some issue, let's say this leader goes down. Okay, so now in this case, these two replicas are only for the reads. They are not configured to accept the writes. So this will make the system go down because there are no database servers that will now accept the reads. The writes. Okay, so this can be solved by one of the way, that is keeping a orchestrator. Okay, let's say we have kept an orchestrator server. The role of the orchestrator server here is to keep an eye on these servers, and if the leader goes down, then it should elect one of a leader among the one that are already available. So among these two, let's say this one is elected as a leader. So now the system is again back. Now this server will again start accepting the reads and writes, and this will be having the replica that will act as a only for the reads. But now there is again a problem here. That is, what if this orchestrator server itself goes down, and post that the leader also goes down? So now how can we again elect a leader or a server that will accept the writes? So now again that's an issue. So these are the two issues that needs to be solved in the distributed systems. So for that reason, we need to go with this solution, that is the leader elections, where the servers, available servers, among them they will elect a leader and they will make sure that system doesn't go down. So this scenario or the problem that we discussed is known as single point of failure. Okay, that is going to make the whole system go down. Okay, so let's move to the next part. So here we have another example where e-commerce application where it is accepting thousands of order per second. So in this case, let's say if we have multiple databases and if we allow all of them to accept the writes, then there can be a chance where the orders may get overridden because multiple databases are trying to accept the writes. So to avoid that, we need to elect a leader that is going to accept all the writes, and the followers will copy the or whatever the data that is written and will act as a read replica. And only there will be one server that will act as a write, or the one that will accept the writes. Okay, so how we can implement that? Let's look at into the next slide. So before that, let's look into a couple of terminologies that we need to understand before we discuss this concept. The first one is node. Here a node signifies a single database server or a single database instance. Next we have the cluster. So here with cluster we mean the group of the nodes. We call it as a cluster. Then we have the heartbeat. So heartbeat is a network, a frequent automated signal sent by the leader saying I am still alive to the followers. So that is nothing but heartbeat. So we will see how we can implement that in the demo. Then we have the consensus. So consensus here is the process of the cluster agreeing on a single state. So when an election happens and they will decide a leader, so for that a consensus has to be made among all the nodes in the cluster. And the next we have the quorum. So the quorum here means the minimum votes required for a decision, strictly a majority, right? So that defines the quorum, that is the minimum votes that are required among the nodes in that cluster. Next we have the split brain scenario, where we are left with a number of nodes that are unable to decide the next leader. Okay, there is a split brain. Because of that, now we have the nodes, but we don't have a leader to accept the writes. Because of that, the system is unable to accept the writes. So that's a split brain scenario. That happens when we usually select the number of nodes in a cluster in an even number. So that's always recommended to select the number of nodes in a cluster to be in an odd number, okay, either 3, 5, 7, like that. Next, here let's understand a couple of things more, that is the node state matrix. So in a Raft consensus algorithm, so for electing the leader in this distributed system, we'll be using an algorithm that is known as Raft consensus algorithm. So here every node in the cluster always inhabits one of these 3 states. So the node can be a follower. It can be a follower when we already have a leader among those nodes. So the role here is as a normal worker. Action is to listen to the leader, then responses to the heartbeat. So here this follower will keep on getting the response heartbeat from the leader. So the moment it doesn't get a heartbeat in the next 50 microsecond, then it will reset its counter so that again so that it can become a candidate. Okay, so let me explain you what is that before next when we discuss about the candidate. So the next one here, the next state is the candidate. So this state comes when there is a no leader. Let's say we have 3 nodes, okay, and this is a state where currently we don't have any leader. So at this moment what happens, every follower have a timer. So they will randomly reset the timer between 150 microseconds to 300 microseconds, okay. So between this number the timer get resets in all the 3 followers simultaneously. And now whichever follower's timer hits 0 first, that follower will take one oath for itself, and then it will make a call to the other 2 nodes to get the oaths. So the moment the other 2 servers get the signal, they will oath for this server, because this server's timer has hit 0 first. So because of that, now this server will get 3 oaths and this will become the leader. So the moment any server's timer hits 0, that server will become as a candidate, okay, or we call it as an aspiring leader. Okay, so there can be a question that what will happen if 2 servers hit 0 at the same time. So now that's a tiebreaker where none of them will get a majority. So at that moment again the timers will get reset, and here as the timer reset time is randomized, so the next time there is no chance that again one of the 2 servers will hit 0, okay. So when there is a tie, there is a re-election immediately, okay. So by that leader gets elected, and finally we'll get a leader that will be the boss, so that coordinates the writes and sends the heartbeats to the followers. So here it is not going to accept any heartbeats, it is going to only emit the heartbeats, that is the signal to the followers, and it disconnects from the cluster or crashes whenever there is some issue, okay. So next, here the engine of consensus, that is a Raft algorithm. So we already discussed this thing, that how the election happens. So every node in the Raft cluster constantly cycles through this logic. So the architecture relies entirely on randomized countdown timers that we just discussed, and their continuous suppression via the heartbeats. So this is how the election happens. So let's discuss this quickly. So in the normal scenario, there are 4 followers and 1 leader, and due to some issue the leader goes down. Now the timer resets, and here you can see that let's say this node's timer hits 0. The moment it hits 0, it will oath itself, and it will ask for the oaths to the followers. Now the followers oaths to this new candidate, and it will become the new leader. So that's a simple algorithm that is used here for the leader selection. So this is nothing but the Raft consensus algorithm. The next one here, the unbroken rule of quorum. So because here the leader cannot be elected, nor can it maintain the power without the strict majority of the cluster supporting them, okay. So in a 5 node cluster, 3 votes are required to pass any decision. So this strict mathematical boundary is the only thing standing between the order and a total system corruption. So this quorum is maintained so that every time a leader is present and it has the other followers. So here let's discuss one of the crisis situation where we'll see whether we'll have a split brain scenario or not. So here we have 5 clusters, 5 nodes in one cluster, and due to a network partition, the 2 nodes get into another network zone, and other 3 nodes get into another zone, and the 2 nodes which are present in the group east is there where the leader is. So now at this moment it will check whenever it needs to replicate the data, that it has to replicate the data to at least a majority. But here it is unable to do it because it has only one node to replicate. So at this moment, it will feel that it will think that there is no majority, and it goes down. That is, now it is not a leader. So the moment that the same thing happens here, where these servers are waiting for the heartbeat from the leader. But now leader is in another network partition, and it is unable to get the heartbeats. So that in that moment, one of them's timer will hit 0, and they will conduct the election. And because here we have the nodes in odd number, one of them will get the majority, and it will become the leader, and it will start accepting the rights. So because of this, the split brain scenario is avoided. Okay. So the next thing here that we already discussed, that is the quorum prevents the split brain. So as in the second, that in the group West, we had 3 nodes, it was able to select a leader, and that prevents the split brain scenario. Next, where we can see this Raft algorithm in real world. So it is implemented in many of the major systems. For example, in the Kubernetes cluster to maintain the leaders. The same algorithm is used. Then in the Zookeeper, that is used in Kafka. So this is where it is again used to maintain a leader that is going to accept the rights. And also in the Consul. So Consul is used in the distributed microservices for the service registry and service discovery. So here when we have one single Consul server, in that case all the service discovery is happening through that one single server. And let's say if that one single Consul server goes down, then the whole microservices architecture comes down, because the microservices will unable to discover each other. So they will be unable to make a inter-service communication. So to avoid that scenario, we usually maintain at least 3 Consul servers, so that if anyone goes down, then there will be a leader election, and one of them will become a leader that will accept all the reads and writes, so that the microservices will able to continue to do the service registry and service discovery. So this is the same algorithm used in these 3 systems. Next, here the odd number rule that we already discussed, that is usually we should never use a even number of servers for load balancing in a consensus cluster. Always use an odd number like 3, 5 or 7. An odd number mathematically eliminates the deadlock situation, ensuring that during any network partition, a tie is impossible, and one side will always retains the quorum, that we already just discussed in one of the previous slide. Okay, so this has to be kept in mind. So the architecture of the resiliency. So here the goal was that eliminate the single point of failure, so that we were able to do it by having multiple nodes and implementing this Raft algorithm. Then the trigger here is the sudden absence of the continuous heartbeats combined with randomized countdown timers. So that will help us to select the next leader. And the safeguard here is that the strict quorum mathematically prevents the split brain. Okay, so next let's look at a simple demo of how we can implement the leader elections for auto recovery in the distributed systems. Okay, so let's look at a demo. So in this demo, we will try to implement what we have just discussed. So here for this demo, I will create a cluster with around 5 nodes in it. So for creating the cluster, I'll be using Docker containers. So I'll use this Docker compose file that will create 5 node Raft cluster. So each service is equal to 1 server in the distributed cluster. So nodes communicate with each other inside the Docker on port 5000, and the demo controller on the host reaches each node via port 50012 to 5005. So these are the 5 ports on which all the 5 containers will be running. And then we will begin with our demo. So let me first run this Docker compose file. Docker compose up build in a detached mode. Okay, so it has started and it has created the nodes. Let's check here. So we can see that the 5 nodes have been created. And now let us start with the demo. So for that reason, I'll run this demo.py file. .py. Okay. So here, as you can see, our demo has started. So here we have 5 Docker containers that are nothing but 5 servers in the distributed cluster. And we will try to implement these 4 scenarios. The first scenario will be the normal operation, where the normal elections will be conducted among these 5 servers, and then they will decide a leader and others will become the follower. Okay, so along with that, we'll subsequently see the other scenarios. So let me first press enter and let's implement the first scenario. Okay, so in the first scenario, when the cluster starts, all 5 nodes begin as followers. So each node has a randomized countdown timer of 3 to 6 seconds. So it varies between 3 to 6 seconds. So whichever node's timer hits 0 first, that will itself select as a candidate, that as we discussed initially, and then it will ask the other 4 nodes for the votes. So since a cluster of 5 needs 3 votes quorum to elect a leader, and then the first candidate is the only one campaigning, so definitely that is the one which is going to get all the votes. Okay, so the leader then sends a heartbeat every 0.6 second to all the followers, saying that I am alive, do not start an election. Okay, so only when any of the node follower stops getting the heartbeat for 0.6 second, then their timer gets resets and it will wait for it to hit 0, and the moment it hits 0, then again the elections will start. So we will see that scenario later. So now if I press enter, you can see that the elections has been completed, and now for the term 1, node 3 has been selected as the leader, and the other 4 are the followers. Okay, so now all of them believe that leader node 3 is the leader. Okay, and here we need to understand the concept of term that will help us to understand further this demo. So the concept of term here is like initially all the nodes, the term number will be set to 0. So then one of them will elect itself as candidate, and it will ask for a vote to the other followers, all other nodes. So when it asks for the votes, the nodes check its term number. So its term number will be 0, and it will be, and the node 3 as the candidate will be asking for the votes for the term 1. So it will check that my term number is 0 and I am getting asked for a vote for the term 1. So it checks that its term is less than what it is being asked. So for that it will give the vote. So if it is reversed, then it is not going to give the votes. So we will see that scenario next. So now every follower has given the vote for the term 1, and now the node 3 has been selected as the leader. Okay, so next we will see in the scenario 2, we will crash the node 3. Okay, we will crash the node 3. The moment it gets crashed, the timeout begins and the campaign starts. Then the quorum is formed, and again one of them is selected as a leader. So now at this moment, when the second campaign starts, at that time it will ask the vote for the term 2. Okay, now every follower has the term number 1, so it will check that I am getting asked for the term 2 votes, so that's the reason they are going to give the votes. So always the follower will check the term number before they are giving the votes, so that they are sure that for which leader they are giving the votes. Because now in the next scenario, when we wake up the node 3 back, now we have crashed it, when we recover it back, the node 3 will now try to get the votes for the to select itself as the leader. So when it will do that, it will be sending the term number as 1, but now all the followers has moved to the term 2. So at this moment they will tell back to the node 3 that we are at term 2, so you need to upgrade your term number. So at that moment it will upgrade its term number, and it will simply like adjust as a follower. It will not contest for the leader selection because it has just woke up. It did not have the memory of the last election. Okay, so that's the importance of the term number. Let me come back to that again. So now in the scenario 2, now we are going to crash the node 3, and then we'll see how automatically the system will come back by selecting a new leader. Okay, sending the crash signal to node 3. Node 3 is down, so the heartbeats have stopped flowing. So followers are counting down their election timer, and what's it like now? If we see here, it has been crashed, and I think node 5 was hit to 0 first, and it asked for the votes. So here you can see now every follower now has got upgraded its term number to 2. But now if you see, the node 3's term number is 1. So then the next step, we will recover the node 3, and at that moment it will think that it will think itself as a candidate, and it will ask for the votes. So the moment it will ask for the vote, the followers will tell it back that you are behind, you need to upgrade the term number and join as a follower. Don't try to elect yourself as a candidate. So that is the importance of the term number. Okay, so now the node 5 won the election, and it is a leader. So this is exactly how the Raft algorithm works. Next, let's move to the next scenario. So we are recovering the node 3. Okay, so the moment the node 3 got recovered, it has automatically joined as a follower, because it cannot be a leader because already we have a leader, that is node 5. Okay, so that's the recovery, and it has automatically joined back into the cluster without any disturbance to the existing system. Okay, so now let's look at the scenario 3. It's a very interesting scenario. Here what we'll do, as we already discussed, what will happen if two nodes simultaneously elect themselves as a candidate, like nominates themselves as a candidate and ask for the votes. So that's the scenario we are trying to implement here. So for that reason, what we'll do, we will first crash the leader, and then we are now left with 4 nodes. And then we will freeze the timer of 2 nodes, okay, and then we'll again resume that at the same time. So now at that moment, both of them will be at time 0, and both of them will elect or nominate themselves as a candidate and ask for the votes. So what will happen, if you see, both node 2 and node 3 becomes candidate at the same time, and the both vote for themselves, and so neither can vote for the other, and then they will ask for the votes to the node 5 and node 4. Okay, so node 4 receives the node 2's request and it gets 1 vote, and node 5 receives the node 3's request and it will also get 1 vote. So at the end, node 2 and 3 gets 2 votes. Both of them are at the equal votes and nobody wins. So now here at this point, both the candidates revert to follower with a fresh random timer. So this time one fires before the other, and the election resolves cleanly in the round 2. Okay, so in the round 1 there is no winner, so they go for the round 2. So we are crashing the node 5 and freezing the election timer, and the trap is now set. Node 2 will run for the election, node 3 will also run for the election, and this is where in the round 1 nobody gets elected. So now you can see firing election for node 2 and node 3 simultaneously, watching the election unfold. So here you can see both candidates failed to reach the quorum. They each received 2 votes less than the required quorum. So Raft handles this gracefully. Both candidates revert to the followers, and each draws a new random timer. The one with the shorter timer will fire the next time, and second round, one candidate sweep the votes and wins the election. So if I go to the next, here you can see the elections has started, and finally one of them become the leader. Okay, so here node 5 is still crashed. Okay, so node 1 won the round 2 cleanly. Now let's go to the next scenario here. So in the scenario 4, we will divide the nodes into the partitions. So to implement the split brain scenario, so the network partition is when the network failure splits the cluster into 2 groups that cannot communicate. So even though all servers are physically running, this is a worst case scenario where the split east group having the node 1, 2 and west group, let's say, having the node 3, 4 and 5. It has 3 nodes. So the danger here is the split brain. If both sides elect a leader, then you have 2 leaders giving conflicting commands simultaneously. This causes a data corruption. So now how Raft prevents it with the quorum, let's see that. So each in the east 2 nodes cannot reach the quorum because at least we need 3 votes, cannot elect a leader. So the east current leader loses heartbeat acknowledgement from the majority and steps down voluntarily. So and the next another section we have the west which has 3 nodes exact quorum can elect a new leader. So only one valid leader exists at any point of time. So split brain is impossible in this quorum, okay, because we have 5 total nodes. So the perfect setup, current leader is the node 1, okay. So the node 1 is the current leader, is in the east minority group. So the east minority group has 2 nodes, the node 1 and node 2, where the leader is present, and then the west majority group has a node 3 and node 3, 4 and 5. So after partitioning, east leaders will detect it can't reach the quorum, so the leader node 1 steps down. So the east will try to elect a new leader but fails, and the west will elect its own leader successfully. So let's see that partition has been applied. We have all of them have now become followers. Among them we got 1 leader, okay. So if you see, the node 1 and 2, which are part of the east group, does not believe in any leader, right? Because at this point they don't have any leader. But these 3 conducted the election, which are in the west group, and among them 1 got selected as a leader, and they believe that node 5 is a leader now. Okay, so that's how the split brain scenario is avoided here. Okay, so now we are here trying to heal them back, and now all of them are fully recovered. Okay, so all cluster fully recovered. Node 5 is the single leader. All 5 nodes are reachable and agree on who is the boss now. Okay, so that's what we needed to discuss here. We have looked into multiple scenarios, how the Raft consensus algorithm works and how the leader is selected. Okay, I hope you are able to understand this whole architecture, how the leader election is done in the distributed systems. Okay, so let's meet in the next video.